Okay, let's go ahead and get started. According to my phone, it's time to start. Logistical things, as you know, there's a problem set due today, and there's a new one posted due in 2 weeks. Remember that in 3 weeks from today, we have the second midterm. That's the last week of classes, okay? So there will be the second midterm 3 weeks from today. And today we're going to do 5-minute project status reports, and we're going to do them at the end, not at the beginning, because I'm afraid that otherwise they will eat up all the available time. So I'm going to allow 50 minutes, and I will start at 11:10. And if I haven't started at 11:10, someone please interrupt me and tell. Not 11:10, 10:10. Thank you. We started at 11:10. We're already late. So just some suggestions. I realize you've already probably thought about what you want to say, but certain key pieces of information that we would like is that if the title of your project has changed, please let us know. Remind us of the names of the people on your team. Remind us of the overall goal of your project, the elevator speech, right? What you're trying to do. By the way, mastering the elevator speech is a really good thing to do. It takes practice, and it can be incredibly valuable when you're out there in the real world. Tell us how you're organized. So in particular, hopefully you have well-defined responsibilities within your group and who's responsible for what, that kind of thing. And what the status of your project is. And is there anything else that I've forgotten to include in that? Okay. Oh yes, your milestones, right. Thank you. Now, I've invited a gentleman from Tektronix who happens to also do some recruiting. So if you're looking for a job, you might contact him afterwards. But anyway, he's interested in what we're doing here, and so he's going to be joining us in a little while, and we'll watch these and maybe ask some questions. Okay. Any questions about logistics or course material or anything else? All right. So to tell you the goal, first let me remind you that on the website there is a schedule of exactly what we're covering and pointers to PDF files for all of these, all of the PowerPoints that we use. And today, this week, we're going to be reverting to Chapter 6, Modeling, and looking at data flow models. And I think that this fits rather nicely with the analysis thread that we've started to focus on in the class, because data flow models are actually very rich and interesting from an analyzability perspective. You can do a lot more in terms of systematic analysis with data flow models than you can with threads. And as a consequence, if you're building safety critical systems or systems that have serious reliability requirements, sometimes using data flow models can yield much better designs than other alternatives to concurrency. So that's what we're going to talk about, and the next problem set has at least one problem that is directly from this material that we're going to be talking about today and Thursday. Okay? So I wanted to just start with a little motivating example. So this is a model in Ptolemy of a system that captures the signal from the microphone on my laptop and does spectral analysis on it and displays the spectrum, right? So that's what you're seeing. On the left is the time domain signal. On the right is the power spectral estimate. You can tell there's a 1 kilohertz whistle, no, 2 kilohertz, right there, okay? The interesting thing about this is that, of course, in order to do spectral analysis, you have to collect a bunch of audio samples, and and then process them in a batch. And in this particular system, there's not a lot of real-time stuff going on because there's no closed loop. It's just gathering information, right? But a lot of real-world applications would actually have closed loop behavior. So for example, spectral analysis might be used in hearing aid design or something of the like. And the interesting thing about this is that the spectral analysis itself is a relatively heavy computational load that can interfere with the real-time processing that you might be doing in parallel, okay? So we'll use that kind of as a motivating example to look at the scenario. So this is a simplified version of that, where in fact there is a simple real-time behavior where you're doing some audio capture and also some audio feedback, some audio playback, okay? And you want to get low latency here, okay? But at the same time, you want to be able to do this spectral analysis, and the computational load of this spectral analysis could interfere with achieving low latency here. In particular, you need some sort of concurrent processing, because if you pause your audio processing in order to do a spectrum analysis on a whole batch of data, then you get gaps in the sound, which are very annoying. Okay, they sound like clicks, and you won't sell the product. Okay, so this is a very simple scenario, but it's a very common situation in embedded systems where you've got some real-time streaming of data going through, and some batch processing that maybe has looser real-time constraints or possibly no real-time constraints at all. Okay. Now, so you've got this time-critical path, and you have this not time-critical path in this scenario. So one possible way to handle this would be using threads, where you simply create two threads, and the not time critical path has lower priority, and the time critical path has higher priority. And of course, you know why you would assign the higher priority. And but an interesting thing is that you need to justify this on some basis, okay? And at the minimum, you need a justification, a theory that handles precedences, because there are precedences here, and they're slightly more complicated precedences than the kinds we've looked at, because of the fact that the spectral analysis requires collecting a batch of data before it can actually do anything. All right, so you actually have to be executing a bunch of these before you can execute this FFT. Okay. So earliest deadline first with precedences can be used in this case. And it will be optimal with respect to feasibility, but how do you assign deadlines? All right, there's some, in order to apply this theory, you've got to come up with some scheme for assigning deadlines to these tasks. And the second question is, how do you implement the communication between the threads? And the communication between the threads runs the risk of creating scheduling anomalies, right? Because this computation cannot execute until you've collected a batch of data into a buffer. All right? Operating on that buffer is going to happen in two distinct threads. As a consequence, you're going to need to use mutual exclusion locks to guard the data in that buffer. As soon as you've got mutual exclusion locks and threads with priorities, you have to worry about whether you're going to get priority inversion or other scheduling anomalies. Okay, so the reasoning of this thing, even in this simple example, can get a little bit tricky. And of course, the real-world examples are not this simple. There's a lot more things going on, different sample rates happening simultaneously, and so on. And the basic point in this class, I think, is that we're not happy with what is in practice the state of the art, which is that people code this up in C, tweak the priorities until it seems to work, try to test the heck out of it, and then ship it. Right? We'd like to examine more principled ways of doing the design. Okay, so abstracting this still further, we assume that we've got three tasks: the blue task labeled A, the green task labeled B, and the red task labeled C. Any colorblind people in the room who can't see the difference between the colors? It's going to be a problem with these slides. I apologize, but if that's the case. Hopefully everyone can see the difference between these colors, okay? But Anyway, so the scenario here is we suppose that C requires 8 data values from A to execute. Now, of course, for spectral analysis, you would typically need much more than that, but the pictures would get ugly if we use much more than that. So, and suppose further that C, which is the stand-in for the spectral analysis, takes a lot longer to execute than A or B. So if we were to just look at this task set and think about just a single execution of each of these, or, well, a minimal execution of each of these tasks, we would need to execute task A 8 times in order to have it produce, assume each execution produces 1 data sample. Okay, so this A might be a wrapper around a sensor that is grabbing a sample from the microphone and producing it on its output. So it needs to execute 8 times. B needs to execute 8 times, and B is the time critical one, we assume. Therefore, it'll be given higher priority than C. But of course, because of the precedences, C is unable to execute until it's collected 8 samples anyway. So the only way that the priority had any effect at all was that the last green task executed before the red task. Okay? Other than that, everything here was determined by precedences. Well, not quite. We could have executed A 8 times right at the beginning before executing any green tasks at all. Okay? That would be another option. But if we assume that the green task has earliest deadlines, it'll be given highest priority, and therefore it'll be executed as soon as the precedences allow for it. So is this scenario clear? Okay. So for the audio example, what's wrong with this picture? Suppose that A is a microphone, B is a speaker, possibly somewhere else in the network or something, but...
You'll play back and then there'll be a pause.
Right. So you'll play back and then there'll be a pause, right? And so was that what you were going to say? Or?
I was going to say that based on the picture you have at the top,
Mm-hmm.
data that goes from blue box to the green box also should be going to the red box.
Right.
So you can go on your schedule. There is no data going to the red one.
Yeah, so that's another potential problem is that, how is this communication actually happening, right? If this guy is just writing to a memory location every time it executes, then C is not going to get anything except perhaps the last data value produced by A. So you need to buffer the data that is produced by A in order to have it accumulate in a buffer for C to use. Okay, that notion of buffering this data is a central notion in the concept of data flow. Okay, so the idea is that you think of A as an actor that produces a chunk of data, and then some other actor consumes that chunk of data. But until that chunk of data gets consumed, it persists. Okay, so C will kind of automatically in this model of computation accumulate input data until it consumes it. But of course you have to provide for that buffering in an implementation. Right? So the implementation is going to have to provide some mechanism to buffer up that data. So these are 2 issues that we have to worry about: the buffering and the pause that would occur because of this schedule. Now, the pause, of course, is an issue because, in a sense, we've naively thought of sort of a minimal execution of these tasks. But in fact, if we're really processing audio data, what we really want to be doing is running these tasks an infinite number of times. None of our scheduling techniques can deal with infinite numbers of tasks, right? So, at least not, directly. You have to worry about that. Okay, so the formulation that we could use is one like this, where we observe the fact that C is going to accumulate 8 data values, so we're going to need a buffer at least of length 8 at its input. And we construct a precedence graph that separates out the individual firings of A and B and the single firing of C, which depends on all the firings of A. Okay, and so here's a precedence graph that shows the tasks that need to execute in order, and this would be the resulting earliest deadline first schedule if you assume that B always has the earliest deadline. Okay? So if we want to implement this in using this data flow model, we have to come up with some sort of a schedule. And there's a couple of different ways we could do this, right? One is to do static scheduling, which is we assign to each thread a sequence of actor invocations and repeat those forever in a single thread. And dynamic scheduling would instead choose every time that a thread becomes idle or resource becomes idle, then a dynamic scheduler would choose which actor to fire next. Okay? These are two rather different strategies that you could use. The principle here, okay, I want to focus a minute on this question of buffering, all right? The principle here is that the communication between these components is a stream. A stream you can think of as a function that maps the natural numbers into some set, which is the data type of that stream communication. Now, notice that in this case, the assumption here is that the stream is infinite. Okay? That's the interesting thing about data flow models as opposed to these finite task scheduling problems that we've looked at so far, is that we're going to be assuming that we're processing infinite streams of data, and we're going to directly confront the scheduling problems for infinite streams of data. Okay? Now, how is this scenario different from LabVIEW? Right? You've all done enough in the lab, I think, to be familiar with LabVIEW. And LabVIEW claims to be a data flow model. Yeah, Apurva. Yeah, so LabVIEW doesn't quite have the same notion of production and consumption of tokens, okay? And in particular, it doesn't have any implicit buffering. So in LabVIEW, every connection between blocks has just enough memory allocated to store one instance of the data type. If you want to accumulate data in a buffer, you have to explicitly construct that buffer as an array, okay? And then you explicitly manage the accumulation of data into that array, and then you use control structures like conditionals or iteration loops to handle the relative rates at which these things fire. In a purely data flow model, so it turns out that LabVIEW is a data flow model, but it's a rather special case of a data flow model, which is often called a homogeneous synchronous data flow model, where every actor consumes and produces a single token. Okay, a single chunk of data. So if you want to accumulate data in buffers, you have to make bigger chunks of data and explicitly manage the buffering. But in addition to that homogeneous synchronous data flow, it also provides these scheduling constructs which give you control over iteration, conditionals, and so on. So it's kind of a hybrid model. It's not a purely data flow model. A purely data flow model just concerns itself with actors producing streams of data, and then downstream actors become enabled by the availability of data at their inputs. And buffering is implicit. Okay? So in a purely data flow model, you would have a FIFO buffer that is conceptually unbounded. In practice, of course, you need to be able to bound it, especially in an embedded system, because running out of memory in mid-flight is not a good thing. Okay? So how you bound the buffers becomes an interesting question. All right, so here's some variants of data flow. So homogeneous synchronous data flow, every actor consumes and produces a single token. Okay, a token can be a data structure of arbitrary size, either a primitive integer value or floating point value or something, or an array, or anything else. Synchronous data flow, every actor produces and consumes a fixed integer number of tokens. So in particular, if I was doing an FFT here, this guy, C, consuming 8 tokens, if it always consumes 8 tokens when it fires, then it is a synchronous data flow actor. And the use exclusively of synchronous data flow actors enables me to do all of the scheduling statically. I can predetermine what the schedule is going to look like, pre-analyze the schedule, pre-allocate the buffers, etc. A much richer style of data flow allows production and consumption of tokens to be data dependent. So in particular, you could have an actor that is a selector, which will, when fired, consume a token from this control port, and it's a Boolean token. And if the value is true, then it will consume a token from this true port. And if the value is false, it will consume a token from this port. Okay? Correspondingly, I could have a switch, which will consume a token at this data input port and a token at its control port. And depending on the value of the token at the control port, will produce an output either on the true or the false port. Okay? Now, what do you think? If you have actors like this in a data flow network, can you do static scheduling? So will I be able to determine exactly what order? If I have an actor feeding the switch and two actors connected as sinks from the switch, yeah.
I don't think we can do static because we don't know what is going to come next.
Right. So you can't quite do static scheduling, right? Because anything downstream of this true port, whether it fires, is going to depend on the values of the tokens provided at this control port. Okay? So an interesting observation is that if you restrict yourself to a NAND gate for a homogeneous synchronous data flow and only Boolean data types, okay, so the inputs and outputs are always Booleans, and this is a NAND gate, and you allow for initial tokens on arcs, and you allow switch and select, you have a Turing equivalent model of computation. You can write any computable function using a NAND gate that consumes and produces a single Boolean token on two inputs, okay, produces a single Boolean output, switch and select, and the ability to initialize a connection with some initial Boolean values. Those four things give you the ability to create a Turing machine, which means you can do any computation that you can do in C or in Haskell or in Java or anything else. All right? So this is, by the way, a notion of a model of computation. Right? A model of computation gives you an underlying set of primitives, and from those primitives you build up computations. And obviously the computations are built up here in a very different way than they would be for a Turing machine. Okay? How many of you know what a Turing machine is? So not so many. So those are the ones that probably have taken 170, I imagine. Did Sanjit talk about it last time? Okay. Maybe Kevin talked about it. Okay. There's a lot of interesting properties of Turing machines, but they're a bit beyond our scope here. I guess in 170 you would learn about the consequences, but there's a couple of interesting consequences of using capabilities like this switch and select. So one of them is that suppose I give you an arbitrary network consisting of these NAND gates, switch and select, and some initial values on the connections between actors. Then an interesting question is, can I find buffer sizes for the connections between actors that are bounded? Turns out that question is undecidable. Okay? There's no algorithm that, given such a network, will always be able to tell you whether the buffers can be bounded in that way. Okay? So that's a consequence of the richness of the model of computation, that you're able to construct a Turing machine from these primitives, and as a consequence, certain things become impossible in principle to solve. That has profound consequences for embedded systems. Right? If you have a data flow model and you can't prove that buffers are bounded, how can you be sure you're not going to run out of memory in mid-flight? Okay? So that's the kind of thing you look for. So one of the things that we like to do when we're using models of computation like this is restrict the model of computation so that static analysis becomes possible, so that you can prove properties about the system. So here's a question for you. Do you think that it's possible for a LabVIEW model to run out of memory because of buffers overflowing and exhausting all available memory? How? It doesn't use buffers, right? So, I mean, every connection between blocks in LabVIEW only requires enough memory to store one chunk of data, whatever data type it is. As a consequence, at least from the perspective of the communication between actors in LabVIEW, the amount of memory that it uses is static, predetermined, totally analyzable. Okay? So do you think you could create a Turing machine in LabVIEW just using a NAND gate as an actor and those buffers? You think yes? I'd like to see it. You can't, actually. And in fact, it's easy to prove that you can't, because no model of computation that is provably uses a bounded amount of memory can implement a Turing machine. Okay? And this LabVIEW, now LabVIEW, of course, you can do arbitrary things inside a block, right? So you can actually create a Turing machine by doing a bunch of fancy stuff inside a block. You could create a block that implements a stack, for example. Okay? But if you constrain the blocks themselves to use finite memory as well, then you can't create a Turing machine in LabVIEW. Okay? Is that a problem? Well, you know, there's a price you pay for that. You've lost something in expressiveness, but there's also a benefit. You can design systems that you can prove will use only a bounded amount of memory no matter how long they execute. That trade-off is a constant trade-off that we face, okay? And in embedded systems, we care a lot about being able to prove that things use a bounded amount of memory. Okay, so the buffers can be implemented as a chunk of memory with a couple of pointers into them. If you restrict yourself to finite length buffers, you restrict the model of computation so that it is no longer as expressive as a Turing machine, and there are programs that you cannot write. Does anybody know what kind of program you can't write? Can anybody give me an example of a program you can't write in a model that uses a provably bounded amount of memory? Yeah. I'm sorry, say it again. Infinite loops are not necessarily a problem, okay, because they could still use a finite amount of memory. And in fact, you know, I mean, even a synchronous data flow model that's processing an infinite stream of data is an infinite loop, and it uses a bounded amount of memory. Printing pi. Now, I don't know whether that could be done with a bounded amount of memory. I would guess that could be done with a bounded amount of memory, but I'm not totally sure. Do you know that to be the case?
That was, I don't know when it was, like maybe a year ago, that was not. So then they random some. Like, the goal was to like prove something about multitasking, like multithreading. So
Right.
you could use that to get avoidance of time.
Yeah. All right, so nobody knows an example? So by the way, I mean, it's a good sign, right? Because, you know, you've written a lot of programs, and you probably are pretty sure that all the programs you've written can execute in a bounded amount of memory, right? So what price have we paid in this loss of expressiveness? Well, maybe not that much, right? But there are things you can't do in principle. So one example is you can't parse a context-free grammar. Okay? So by a context-free grammar, I mean, for example, the grammar that defines expressions in C. If you want to write a parser that can handle an expression of arbitrary length in C, then you cannot write a parser that will provably execute in it with a bounded amount of memory, okay, and parse that arbitrary expression of arbitrary length. All right? So there is a price you pay. There are certain things you can't do. But there's an enormous benefit when you can bound the computation. So LabVIEW exploits this, by the way. So for example, when you synthesize embedded software from LabVIEW or you synthesize an FPGA implementation, it uses a bounded amount of memory, guaranteed. Okay. All right, so at this point we have 50 minutes available, so I'd like to switch to the project status reports. And Kevin, I think, has PowerPoint slides loaded up onto this laptop. Is that right? Let me move this over there. You want to connect that up? So I think Sarah made the suggestion that we reverse the order. So if you don't like that, you can blame her. So can you reverse the order of your PowerPoint slides?
Go backwards through it.
Let me, can I swing this under you?
I have more slides on here to send to you, but they should exist.
We can, I think we can just connect up your laptop. You know, we're trying to avoid it wasting too much time, but you know, if only, yeah, as long as most of them are on here. All right, so I think at this point, if anybody is listening to screen capture, I'm going to turn off the audio on screen capture because I think it would be a hassle to pass around this microphone, and I don't know. Or do you guys want this recorded for posterity? No. No. Okay. So we will turn.